All right, welcome everybody to our first week of our biochemistry weekly reviews. So these will be held every Wednesday from 4 to 5:15 p.m. If you can't attend, that's completely okay. We understand that everyone is busy and has their own things to do at various times. These reviews will be recorded and uploaded to YouTube. But if you can't attend live, I think it's preferable you can ask questions live and things like that. I think I've forgotten to introduce myself. My name is Mina. I'll be one of the tutors for biochem. Additionally, if you have any questions after the review, or if you want to come to our drop-in tutoring, I will personally be there Monday mornings, as well as Wednesday evenings right after this review until we close. So with kind of that introduction out of the way, I think I'm just going to jump right in. So this is kind of an introductory week of making sure you guys know the basic information just so we can deal with it. So I'm just going to jump right into chapter 1. It is split by chapter at first, but toward the end of this, I'm going to stop splitting it by chapter and more into kind of groups of concepts, if that makes sense. So for just this first question, ranking the weak chemical forces by relative strengths. So by weak, we mean not covalent, basically, because covalent bonds are a lot stronger. So we have hydrophobic bonds, ionic bonds, hydrogen bonds, and van der Waals attractions. So just a very quick recap of each of these. Van der Waals forces are caused by the instantaneous dipole. If you guys remember back to Gen Chem 1, instantaneous dipole. And they're generally very, very weak forces. They're very weak forces that tend to be around in pretty much every molecule, every atom, everything. Hydrogen bonds are very strong, and they occur between hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen. And these bonds are caused by the very, very strong difference in polarity, which gives this hydrogen a very strong partial charge, and the more electronegative one, whether it's fluorine, oxygen, or nitrogen, a very strong negative charge. I apologize, that should be negative. And as a result, when this encounters another hydrogen with that same partial positive charge from a bond, it tends to, where's the full screen? Oh, there it is. There we go. So when it comes close to another hydrogen, it tends to form a very strong bond. Ionic bonds are exactly like they sound. They are bonds between ions. So the most common one we most likely will be seeing is sodium ions and chloride ions, and they form sodium chloride, which is kept together by electrostatic interactions. Finally, we have hydrophobic bonds. Hydrophobic bonds are between basically the organic materials you learned about in organic chemistry, so something like butane and butane on top of each other, things like that. They tend to have some hydrophobic interaction between them. So in terms of ranking these, the biggest thing to remember is that our van der Waals forces are our weakest forces. These guys are always present, and they're not particularly strong. They're just there because they have some attractive properties. Going in order, next we see hydrogen. Hydrogen bonding is next. With respect to hydrogen bonding and ionic bonding, hydrogen bonds are a very strong dipole-dipole interaction, but these dipole-dipole interactions are built on this idea of partial charges. So, and I'm just going to assign a number here. If it's a partial charge, so maybe it's a negative 0.7 and a positive 0.4, let's say. Well, ionic bond, positive 1 and a negative 1. So just in terms of the values, ionic bonds, the charges there are stronger, significantly stronger, and so they tend to be stronger than hydrogen bonds. And that's another way we can tell this, although in this case, yes, sorry. So in this case, C and D could be ruled out just by that concept there. I apologize, and A could be ruled out. And so B is really the only one left based on just the van der Waals, but also based on this idea of ionic bonds being stronger than hydrogen bonds. Finally, hydrophobic bonds tend to be the strongest, And this is in large part because of the fact that hydrophobic bonds tend to come kind of in groups. So when I drew this example of butane, of two butanes up here, you have to remember that there are this carbon and its 3 hydrogens, this carbon and its 2 hydrogens, this carbon and its 2 hydrogens, this carbon and its 3 hydrogens. Them on top of each other, hydrophobic bonds tend to be very, very numerous. And so because of that, they tend to be stronger. Okay? So based on a van der Waals energy profile, which of the following is false? And this is for number 2. So before we get into these choices, I'd like to actually show the van der Waals diagram energy profile. It's got a million names. I'm probably just going to call it a van der Waals plot just for convenience. So if we notice, this is the radius in nanometers. To be more specific, this is the difference in, I'm not sure exactly how to word it, but this is the distance the nuclei are apart. Okay? So in other words, if you have one nucleus, or if you have one atom here and one atom here, and these are their nuclei, and actually I want to change color for this. R is this unit in red. Okay? And the reason that is, or I should say the reason that this is important is because it affects the energy profile significantly. So let's talk about it. So if you notice, it doesn't go to 0. Like there's not a contact distance, as it calls it. The graph doesn't exist with an x value of 0. In fact, it doesn't exist with an x value that's very low. It goes down to about 0.3, maybe 0.25, but it doesn't go lower than that. And the reason for that is because it's exactly based on this, excuse me, it's based on that concept that I drew to the right. At some point, they can't get any closer. And so the nuclei, there are things in the way of the nuclei. Obviously, there are the electrons floating around and everything else. And so this tells us basically there's a term for it. If I want to say it's the minimum distance. Don't quote me on that. I apologize. I believe it's the minimum distance, but I don't have it. I don't have the exact term, so I don't give you the wrong information. Okay. So this is at the very top here, I should say, like closer to here, is the closest two atoms can be to one another. Okay. There. Okay. So breaking bonds takes energy, forming bonds releases energy. So now this is important because we're going to get into the y-axis, energy. So if forming a bond releases energy, then any time the energy is negative, there's a bond. In other words, this part right here, if I can just shade it even, this is where there's a bond. So this would be the ideal distance between these two nuclei. So if this is 2 hydrogen nuclei, they should be about 0.4 nanometers away. They can be 0.35 nanometers away, maybe that's here. They can be 0.5 nanometers away, maybe that's here. But being 0.4 nanometers away is their most stable energy conformation. Okay? Yeah, okay. So now let's get into the actual question that was asked. Which of the following is false? The line will never cross the y-axis. Well, that's true because these two can never be touching. Okay? The energy tends towards 0 as the distance increases because the atoms are too far away to bond. So this is something that I never really mentioned, but if we notice, it kind of levels off and it stays here, exactly like it says here, as distance increases. And the reason is because as two atoms get further and further and further away from each other, they stop affecting each other, right? We know that two atoms will affect each other if they're very close to each other. They'll have some kind of intermolecular force, even if it's just a van der Waals interaction. But the further away they are, the weaker the interaction gets. So eventually, from infinitely far away, there will be zero energy between them, and so there will be no chance for a bond, basically. All right. C, the negative energy is from a bond being broken. D, the positive energy is the bond being formed. So both of these kind of go hand in hand, so they both have to be true. Wait, I believe I have this backwards. Oh, wait, yes, wait, sorry, yes, they are both true. Yes, that's exactly right. And then finally, this is false. A bond can form when the atoms are significantly far apart. No, because like we talked about with B, when it gets too far away, they just can't affect each other anymore. Okay, and scrolled ahead a little too far, but that's okay. So what are the most abundant atoms in the human body in order from most to least abundant? This is something that isn't always asked about. It's something that's interesting to know, and it's something that can be valuable. I've seen it asked before. It's not always asked, so I just wanted to include it to make sure you guys at least saw it. So nitrogen, between these four, I should say, of the four most abundant, nitrogen is the least abundant. So just because of that, we can cross out C and D. Hydrogen is the most abundant. And if we think about everything you learned in organic chemistry, with carbon having 2 hydrogens attached to it, or 3 hydrogens attached to it, or however many hydrogens, hydrogen is everywhere. Alcohols all have hydrogens attached to them. And so whenever you see an oxygen or a carbon, you're probably going to have hydrogen not too far away. So because of that, that's kind of why that is. Next most abundant is actually oxygen and not carbon. This is something that I think I see a lot of people make that mistake. Oxygen is second, carbon is third. Okay, that's something to just be aware of. All right, the next question, number 4. What is the general form of an amino acid? So the reason this question is included is because you have to memorize your amino acids. So, and that's going to be a little bit more next week's and the following week, if I'm not mistaken. Primarily next week, we're going to be talking about amino acids, but I thought I'd mention it here just to kind of introduce the concept to make sure that it gets covered at some point when you guys have a chance to memorize it. Oh, excuse me. Okay, so the general form of an amino acid is you have your central carbon, you have a hydrogen, you have a carboxylic group, COOH, and you have an amine group, NH2. And finally, you have this R group, okay? This R group is a variable group. What that means is every amino acid has this part in blue. Every single one is going to have that. The R group changes depending on the amino acid. So, and I'm not changing color just for convenience because that would take a while. This is glycine. Its R group is just a hydrogen. This is alanine. Alanine's R group is a CH3. Everything else remains the same. Their R group changes. Okay? Apologies. Sometimes it can be hard to just move it. There we go. Okay. So in this question, it is not A because it doesn't have 2 hydrogens necessarily. Not B because it's not a peroxy acid. C is correct, and D is incorrect because it's not an amide. Okay, so that's some of the most important highlights from chapter 1. There is a lot more in chapter 1, obviously, but those are the ones that I think are the most important to know, both for your exam and so that you can do well for the next few topics. Okay, so in the following figure, how are hydrogen bonds represented? So let's take a look. So there's a lot here. Let me erase that, I apologize. Okay, so like we talked about, hydrogen bonds are intermolecular. That means they are between molecules. This is something that I think is very easy to make the mistake of, but basically, this is one water molecule, which means that this cannot be a hydrogen bond, because hydrogen bonds are between two different molecules. So that molecule and this molecule, this dotted line is a hydrogen bond. Okay, and that kind of gives it away, the dashed lines between oxygen and hydrogen. Could there be dashed lines between hydrogen and hydrogen? Yes. Those would not be hydrogen bonds though. Why? Because hydrogen bonds are specifically between this partial positive charge and, actually, I'm going to draw it with this one, this partial positive charge and this partial negative charge. These two are what make a hydrogen bond and not just a dipole-dipole interaction. If maybe you had a hydrogen up here, it and this hydrogen and this one could interact, and there could be a dashed line between them, it would not be a hydrogen bond. So that's a really important thing to keep in mind. Okay. Oh, this one. Okay. So this is a figure that I have seen on some exams, but I have a million questions from students, and I was really confused about it myself when I took biochem last year. So I wanted to go over it very briefly and just make sure we were all kind of understanding what it is and what it means. Okay. So the y-axis of this figure is, milliequivalents per liter. Okay. So obviously milliequivalents isn't a unit we're very familiar with. It's not really a unit, it's just for convenience. Think of it almost like millimoles. Think of it almost like milligrams. Think of it as just some unit for the quantity that we have, and then over liter. So moles per liter, grams per liter, whatever that is, that's a unit of concentration. In other words, what this thing is really telling us is concentration. Okay? And then our x-axis, it's not really an axis, but it's just telling us in the blood plasma, this is what we're looking at. In the interstitial fluid, in the cell fluid, this is what we're looking at. Okay? So this question asks us about the cell fluid. I'm going to talk about the blood plasma first as an example, and then we'll actually try to answer the cell fluid question. Okay? So what we see here is that the concentration of magnesium in the blood plasma is somewhere between 0 and maybe 3 milliequivalents. So the concentration is somewhere between 0 and 3. Calcium, somewhere between 3 and maybe 10. Potassium, maybe 10 to 15. Sodium is very, very concentrated, and it can go all the way up to maybe 165. HCO3, which is carbonic acid. It's also the buffer system of our blood, just for the record, which is why it's where it is somewhere between 165 and let's say 168 as an approximation. So given that carbonic acid is our blood buffer system, it's got a very, very, very narrow band. It's only ever this concentrated. It doesn't have a wide band like sodium to where it can be really concentrated or it can be kind of dilute. It's very concentrated all the time. Okay. And we see that pretty much in all of these examples, right? Carbonic acid is very concentrated in every case, and it's got a very narrow band in every case. Okay. So now let's look at the cell fluid. So in this case, we're only comparing cations. So potassium, magnesium, calcium, and sodium. So magnesium in the cell fluid is, right here. Then sodium, potassium, and I don't actually see calcium. So the answer to this one would be potassium. One thing that I forgot to mention with this is, generally speaking, the cations have their own column, the anions have their own column. So proteins generally tend to be negative, which is why they're on the anion column. And then when you have something like non-electrolytes that don't take an ionic charge, and you have something like carbonic acid, which is neutral, they kind of just go over top or maybe in the middle if that was where their concentration would lie. Okay, all right. Which of the following explains why pepsin is most effective in the stomach? So these are 3 graphs, 3 different enzymes or I should say, of the enzymatic activity of 3 different enzymes at various pHs. Okay, so one of the concepts that we talk about a lot in biochem is enzyme kinetics, is this idea that enzymes are more effective at certain points for various reasons, less effective at various points for certain reasons. It's one of my personal favorite topics. I love enzyme kinetics a lot. And we're going to spend quite a bit of time on it in a month or two. Closer to a month. Anyways, so the key here is that as we notice, this enzymatic activity, excuse me, is pH dependent. Looking at, actually, we'll not look at pepsin because pepsin is what we're being asked about. We'll look at lysozyme. Lysozyme is a great example. At a pH of, we'll call that 2.5 to 2.8, maybe 2.7, there's 0 enzyme activity. Once you get above that, the activity starts to increase until you reach this point. This point is the optimum pH for lysozyme, okay? And it's somewhere close to, let's see, not really sure, maybe 5.5 as an approximation. And then it starts to get less effective. So the reason for this is at this point, the active site of the enzyme is most stable. Okay? When you're over this way, it's too acidic, and some of your enzyme active site will degrade, denature. There's a million different names that are used for it. And over on this side, it's too basic, and the same thing happens. Okay? So why is it that it's on a curve? It's a question I asked myself as well. And the reason is we're not just dealing with 1 or 2 enzymes. We put in some concentration of enzyme, 100 enzyme molecules, 150, 1,000, however many, and we noticed that most of our enzyme active sites were denatured at various pHs. So what we see here is we have a 100%, close to 100%, I should say, active site denaturation above a pH of 8, below a pH of 3. Once you get to like maybe 4 and somewhere around 6.5 to 7, maybe about half of our enzyme will active sites tend to denature and the other half don't. And then once you get all the way closer to 0.5, you see 100% efficacy. Okay, so compare that to pepsin, which is what we've been talking about. Same graph, except if we notice the optimum pH is 3-ish. I'm going to call it 3 just for convenience. So why is that? So the stomach is not the only place that substrates are found in, right? Because pepsin is a digestive enzyme. So as it goes down, the food is in our esophagus, it's in our stomach, intestines, all that stuff. So the other 3 of these answers, A, B, and D, are all true. Pepsin is pretty much only active after we eat. Enzyme activity is dependent on temperature, and enzyme activity is dependent on pH. But only one of them explains why specifically pepsin is most effective in the stomach. And the reason is that it's pH dependent. Our stomach has a pH that's very, very acidic, close to a pH of 3. And so pepsin is very effective in the stomach. But, and this is kind of the brilliance of the human body, let's say something happens to your stomach, there's a hole in it or something like that. God forbid, obviously. Well, the rest of the body's pH is 7. So if we draw that graph out to 7, 0 efficiency. So pepsin isn't going to be degrading at all of our muscles and our skin and everything, just because it's got very little efficiency once we're past that point. Okay. All right. So, excuse me. So these next few questions are going to be a lot more kind of Gen Chem 1 revision and Gen Chem 2 revision as well. And they're about buffers, they're about pHs, pKa's, all that stuff. So when are buffers most effective? The correct answer here is C, and I hope that's kind of memorable. So if I have a pKa of somewhere around, let's say, 6. If that's what the acid that I'm using has, then it's best as a buffer between pHs of 5 and 7. And the reason is between those two pHs, it's got a good ratio of acid to conjugate base. And so as a result, it can kind of interconvert between these two without significantly affecting the pH. Okay. Number 5, which has a higher pH, 0.1 molar of HCl or 0.1 molar of acetic acid. So we've got the same concentrations. We know that this is an acid and HCl is hydrochloric acid, so we're dealing with acids in both cases. So they're equal, right? Not equal. And the reason they're not equal is because this is a strong acid and this is a weak acid. So the basic definition of strong and weak acids, just again, more revision from Gen Chem 1, is a strong acid dissociates completely. So the formula that I would, or not the formula, the equation, the chemical formula, would be HCl, single arrow, H plus, and Cl minus. Weak acids do not dissociate completely. There we go. So acetic acid is CH3COOH, double arrows, so we're dealing with an equilibrium. And it'll be COO minus. Okay. So we can answer the question, but I just very briefly like to describe kind of the thought process behind each of these. I should say I'd rather explain it with these formulas than just thinking it through over at the question. So if we think about 0.1 molar of HCl, let's say in 1 liter, so 0.1 moles. Those 0.1 moles will dissociate completely into 0.1 moles of this and 0.1 moles of this. So how much H plus do we have in solution? 0.1 moles. If we have 0.1 moles here, on the other hand, maybe we'll get 0.05 moles of each of these and 0.95 moles left over here. So what is our concentration of H plus? Significantly lower. So the H plus concentration of a strong acid is significantly greater than the H plus concentration of a weak acid at the same concentration. So even though these are both 0.1 molar, this dissociates a lot less. Okay. So on to this question. Which one will have a higher pH? So this is a very easy mistake to make. I'm not ashamed to admit that I've made it several times. The answer here is acetic acid and not hydrochloric acid. The higher pH means more basic, less acidic, or less acidic. Okay. All right, and we're actually going to figure out what that pH would be so we can compare them in this very next question. So what is the pH of the solution of 0.1 molar acetic acid? And it gives us the pKa. So I'm going to solve this in a couple of different ways, just so that we can kind of show you guys the process. And you guys can do whichever you prefer. So the first thing that we can do is write out the equation. So you're going to see a lot of whatever acid here, propionic acid, and maybe you won't know the equation. So for convenience, I tend to do HA, double arrow, H plus A minus. And A is just some acid. It doesn't matter what it is. In this case, we can think of it as acetic acid or acetate. So The first way we can do this is with an ice table. And actually, I'm going to redraw that so I have a little bit more room to work. So I apologize if this is a little bit boring. I know it's a review of Gen Chem. I just want to make sure that everyone's on the same page. I, standing for initial, tells us what concentration are we starting with. 0.1 molar, 0, and 0. And a big thing to remember, ice tables are concentration, not moles. Concentration, so 0.1 molar. C, change, is this reaction has to go to the right because there's nothing on the right side. So this is going to decrease by some amount, and these are going to increase by that same amount. Okay, and so E is equilibrium, or I think of it as equals because we almost just treat these as equations and add them straight down. So 0.1 plus a negative x, 0 plus x or just x, 0 plus x or just x. Okay, and then we're going to plug it into the equation Ka equals concentration of H plus times concentration of A minus over concentration of HA. Okay. So Ka, and we have the pKa. That's the next important thing to keep in mind. And hydrogen concentration. And so if I want to convert between the two, I'm going to take my 4.75, turn it into a negative number, so negative 4.75, and make that the exponent. And the base is going to be 10. So it'll be 10 to the negative 4.75. Okay. And the number we get out of that is, and oh, I should have written that, I apologize. pKa to Ka, you're going to say Ka equals 10 to the negative pKa. Okay, so okay, there we go. I apologize. So in this case, the Ka is going to equal 1.78 times 10 to the negative fifth. Okay, and now I'm going to plug it in to there. I apologize. So I'm going to say, so I'm going to say 1.78 times 10 to the negative fifth is equal to concentration of H plus, as we see in this ice table. H plus is X. Okay. A minus is also X. And finally, that's all over 0.1 minus X. So now there are a couple of ways to solve from here. So I'm going to, again, show two different ways, though I'm probably going to stop halfway through one. The first way is just pure algebra. So we are going to, apologize, I need more room. So we're going to multiply these two together and also multiply 0.1 minus x to both sides to get rid of this. So 1.78 times 10 to the negative fifth times 0.1 minus x equals x squared. I'm going to distribute this number into both, into both of these terms. I'm going to get x squared equals 1.78 times 10 to the negative fifth times 0.1 minus 1.78 times 10 to the negative fifth times x. From here, I would move everything to one side and use the quadratic formula. I don't want to do that. And I'm assuming you guys probably won't either if you're in an exam, if you're trying to finish your homework quickly, whatever the case may be. It's not fun to have to do the quadratic formula with all of this. So there's an assumption that we use quite often in this class, and it's called the small x approximation. Okay? And this is done basically when you have something minus x or something plus x. And it's almost always going to be in this denominator with this setup of question, which is pretty common. So the rationale behind this comes from the idea that x is going to be very small. So if x were something like, and this is a hypothetical, so actually let me change colors so that I don't get anyone confused. if x were something like 0.000001, however many zeros, 0.1 minus this is close enough to 0.1 that we can just kind of ignore this. We're not going to ignore it completely. We are going to come back to it, but it's done in such a way. And actually, I'll keep writing in red to show this approximation. So it's done in such that we can say, because it's not going to affect our answer significantly, we're going to assume that this number is close enough to 0.1, and then we'll check our work later. So now we solve this. So we would multiply 0.1 to both sides and then take the square root. You guys know how to do that just using your calculator. The number that we get out of this is 0.00133. So x equals 0.0013. Okay, so I'm going to write that in scientific notation. 1.33 times 10 to the negative. Okay, and this is in molar. This is molarity because everything has been in molarity so far. Okay, so this would be our concentration, because remember x from over here is the concentration of H plus and the concentration of A minus. So this would be our concentration. So great, we got the answer. However, we have to check our work. When we use the small x approximation, we have to make sure that this was valid. So the way that we do that is we take the number that we just got, so x, and we divide it by this original number. So the number that we subtracted it from, 0.1. And what we're looking for is a number less than 5%. So if you want, you can include this times 100%. I got 1.3% from this. That's less than 5%. And again, the rationale here, if x is less than 5% of 0.1 of whatever we were subtracting from, it's small enough that we can consider it negligible. In this case, it's 1.3%. It's close enough to negligible that it's okay. And so because we've done that, I should say because we've checked this and the assumption is valid, this is fine as our answer. Okay? So now let's go back to our original question. What is the pH of the solution? So the pH of the solution is equal to the negative log of the concentration of H plus in that solution. So the concentration of H plus in that solution is equal to X. In other words, we take this number, plug it into here, and we get our pH. So, okay, yes, sorry, I apologize. I wanted to make sure that I hadn't taken the number divided by 0.1. My notes are a little bit messy here. So I'm going to take this, I'm going to take the logarithm, and it's going to be negative if we make it positive. The number that I get out of this is 2.88. Okay, that is our pH. And basically from this point, I actually could have started writing in black again, because we're no longer assuming something. This is close enough that it's okay, that it's valid. Okay. However, even using the small x approximation, I had to do an ice table. And then I had to convert my pKa to a Ka. And then I had to do the small x approximation and check the small x approximation. It just seems like a lot of work. So I'm going to show you guys the easier way. And yes, I'm going to work in this area. So the easier way is using one of what I'm hoping will be your favorite formulas by the end of this semester, the Henderson-Hasselbalch Equation. Hasselbalch Equation. So there's kind of a few different ways to write it. I'm going to write it the way that I personally know how to use it. You might have learned a different variant which just adds or subtracts differently and flips and reciprocates a few things. They're all pretty much the same, so just use whatever you're most comfortable with. Okay. So the formula is pH equals pKa plus the log oh, I'm in the wrong window. Okay, sorry, something just popped up. Of the conjugate, let me make sure I don't misspeak. The conjugate base over the weak acid, or in general, of the acid over the base. Or, I apologize. I'm just going to write it so that I don't keep misspeaking. So this is the formula that I memorized. So in this case, HA is the weak acid. A minus is the conjugate base of the weak acid. Okay, so let me show you how easy this formula is using the Henderson-Hasselbalch equation. So I'm going to write this out. So we know that we're starting with 0.1 molar, and we need to find the pH. I apologize. Okay, so pKa 4.75, easy. Concentration of A minus and HA, a little bit less easy, but we're going to just set up the ice table that we did before. For the sake of convenience, I'm going to go a little bit quicker. Uh, 0.1, 0, 0, minus x, x, and x. 0.1 minus x, x, x. Okay. A minus is x. HA is 0.1 minus x. So I'm going to plug those into there. pH equals 4.75 plus the log of x over 0.1 minus x. Okay. So you guys are probably thinking we have two unknowns, we can't really solve this. And you're mostly right. But we can go through this process of the smallest approximation if we wanted to get that number once again. So I suppose this would be better phrased as this is an alternative to plugging it into the logarithm. I'm going to show you guys. So this is going to be 1.33 times 10 to the negative third. 0.1 minus that is 0.099. And we're going to put that in the log. Okay. So what we end up getting out of this is, sorry, I got a little bit lost in my notes. Negative 0.87. I might have miswrote something. It just occurred to me, I don't think this number, I think I made a mistake in this number. Let me double check. Ah, I did something over here. Yes, put in the wrong number. Okay, sorry, I plugged in the number wrong. So this number ends up being negative 1.87. This is 4.75. When we plug it in, we get pH of 2.88. So this is one way to use the Henderson-Hasselbalch equation, but the next question is where you really get to see it shine. Okay. So, okay, there we go. I apologize, I wasn't scrolling very well. So number 7, a solution of acetic acid has a pH of 6.75. The ratio of acid to conjugate base is blank. Okay, so let's think about this with respect to the Henderson-Hasselbalch equation. pH equals pKa plus log base over acid. Okay, it's asking us for a ratio now. So if I were to solve this using ice tables, basically, I would effectively do what we did for number 6 backwards. So I would say, given this pH, what's our concentration of H+? given this concentration of H plus and the pKa or Ka, which we know, what had to be this concentration down here, kind of setting up the ice table, and it's just kind of a process. But the ratio of acid to conjugate base is HA over A minus. Well, that's kind of the same as this thing, just flipped. In other words, we have this thing. Log is just an operator, so we can very easily get to this, and then we're just one step away from solving this. So when I set this up, the way that I would set this up is 6.75 equals 4.75 plus log of A minus over HA. Okay, subtract this. 2 equals the log of this thing. Well, 10 to the whatever to cancel out the logarithm. So we get 100 is equal to the ratio of the conjugate base to the acid. And then from here, to get to the ratio of the acid to the conjugate base, we just put it over 1. In other words, 1 over 100. That's it. Easy. Done. So, in my opinion, the Henderson-Hasselbalch equation is a very, very important tool to keep with you, especially as you guys see some of the reactions that will be, I shouldn't say reactions, some of the questions and the like that we'll be seeing in the next week or so. Okay, so I've only got a few more questions for you all. So number 8, or I should say, before we start number 8, numbers 8 and 9 will be relevant. We'll have this information for us. So the past few questions we've been using acetic acid, which is a weak acid. Now we'll be dealing with ammonia, which is a weak base, and so we're dealing with its Kb. Okay. So just before we start, we see that the terms that are thrown around here is equivalence point. So the term equivalence point has a very specific meaning, and that meaning is moles of H plus equal moles of OH minus. Okay. This is set up kind of from like the titrations that you might have done in Gen Chem 1. So it's when your mole amounts, and H plus and OH minus are for convenience. Really, it should be moles of acid and moles of base. Okay. So if we can set up the equation of volume of acid times molarity of acid equals volume of base times molarity of base, we have the volume and molarity of base, and we have the molarity of acid. In other words, the volume of acid is equal to, I'm just going to divide by mass of the molarity, excuse me, of the acid. So 0.18 molar times 50 milliliters over 0.36 molar gives us our volume. And you're going to plug it into your calculator, you're going to get the number out of it. That number ends up being 25 milliliters. In other words, we need to add 25 milliliters of our 0.36 molar hydrochloric acid to reach the equivalence point. Okay. So now I know what everyone is thinking. The next question is kind of stupid. Wouldn't the pH just be 7? We've added the same number of moles of each of them. And as much as I wish that were the case, when you have a weak acid or a weak base, it gets complicated. And so what I always like to do is I ask myself, what reaction did we just do and what's present in solution? So the reaction that we just did completely reacted our NH3 with H+. Yes, there was Cl-, but it's a spectator that we don't care about. And so what we got out of it is NH4+, ammonium. And more importantly than the name is the fact that if this is a weak base, this is its conjugate acid. In other words, we now have an acid in our solution, so our pH is not going to be exactly 7. So this is where we, what's the word that I'm looking for? This is where there's a bit of a process. So in order to get the new pH, we need our moles of H+. In order to get our moles of H+, or I should say of acid in general, in order to get to acid, we need I personally prefer to keep it H+. In hindsight, I'd like to keep it that way. In order to get to that, we need our moles of H+ over our volume. Okay, so now we know what we're looking for. The volume is the easy part. We had 50 milliliters, we added 25 to it. The volume is the sum of those two. I cannot tell you how many times I've used 50 and gotten the question wrong, or used 25 and gotten the question wrong. We have to remember that since we've added two volumes, we now take the total volume. Total, okay? That's very, very important. All right, and now our moles of H+. So the moles of H+ are going to be how much will dissociate from our NH4. So we need to know NH3. So in order to do this, we need an ice table. In order to get the ice table, we need to know what our molarity of NH4 is. So we reacted 25 times 0.36 effectively. So the reason I moles. And that's what we need. So this tells us we have 9 moles over that 75 milliliters. So 9.075 gives us our concentration of 120. So that's our concentration of ammonium, not our concentration of H+. That comes next, unfortunately. So these are 0 and 0. Oh, and did I label it? No, I didn't. So I need to label this that it's an ice table. We're going to subtract x, add x, and add x. And so we get 120 minus x, x, and x. So now, what Ka are we going to use? We're given a Kb of ammonia. We don't have a Ka. In order to get that Ka, we use what's called Kw. Kw is 10 to the 14th, or I'm sorry, 10 to the negative 14th. And basically, Ka times Kb will equal Kw. So 10 to the negative 14th divided by Ka gives us Kb. 10 to the negative 14th divided by Kb gives us Ka. Okay, so given that, we can convert our Kb into a Ka, which will be, sorry, I need my notes. I did something wrong. So give me one moment. I apologize. I need to redo my notes. I need to redo this math, unfortunately. I apologize. So 10 to the minus 14th divided by that 5.65 times 10 to the negative 10th. Okay, now that we have all the information we need, let's do it. 5.65 times 10 to the minus 10th equals x squared over 120 minus x. So I'm going to do this in red because I believe Alex approximation, but we have to be sure. So I'm going to say that that's effectively 0, and then I'm going to solve from there. So I'm going to take my 5.65 times 10 to the negative 10th, multiply by 120, and then take the square root of this number. And when I've done that, I get x equal to 2.6 times 10 to the negative 4th, negative 4th, excuse me. And then I have to make sure that my small x approximation was valid, so I'm going to take that and divide by 120 and multiply by 100%. As a result, I get some number times 10 to the negative 6th, definitely less than 5% is kind of the point. We don't need to know much more than that. In other words, this number is valid and I no longer need to be in red because I'm not iffy anymore. I'm certain this is correct. Okay, so now I have my concentration of H+. I can now plug that in, so let's go back. So we've dealt with our volume step, right? The volume step was how we 20. Now we have our molarity of H+. We can plug that into the log. So negative log H+ equals pH plug that number into there to get to, I apologize, I have to redo this question, so it will take me one moment. 3.58. Okay. That was a bit of a tedious problem. Okay. So there is a little bit more, or I should say there's probably a lot more that we can do with acids and bases and stuff, but I'm going to be saving that until next week when we've done a little bit more with amino acids. That way I can give you a little bit more of I can give you guys some more relevant questions to do. In the meantime, we're going to kind of shift gears completely and talk about thermodynamics. So we combine these two concepts quite often, and you guys learned this in Gen Chem 2, so I do have to bring it up again. I apologize. But what I want to cover today, it's very short, 5 questions. But basically, it's going to just be a little bit of the overview of the formulas we use so that next week we can kind of jump into the delta G stuff that we deal with. So the second law of thermodynamics, just very briefly, is the universe tends toward disorder or entropy. Okay. And the reason this is important, I've seen it asked a few times. It's not commonly asked, but it can be. Okay, so number 2 is the table. And this, based on the formula, delta G is equal to delta H minus T delta S. Okay, so based on that, we can predict a pattern for what delta G will be depending on the signs of delta H and delta S. So if delta H is positive and delta S is positive, it's going to effectively be some big positive number minus some big positive number. Positive minus positive. In other words, it's going to be temperature dependent. At a high temperature, at high temperatures, delta G will be less than 0, right? Because if temperature is 100 versus if temperature is 1000, as temperature increases, this number gets bigger. And so whatever 100 minus 1000 is going to give us a negative number. And just to recap, negative delta G equals spontaneous. Okay, I apologize if I didn't introduce that earlier. Delta G is our Gibbs free energy, and so the more negative it is, the more spontaneous reaction is. Okay, so if delta H is positive and delta S is positive, then what we're doing is we're saying, and delta S is negative, then what we're doing is we're saying a positive minus a negative. In other words, a positive plus a positive. In other words, never spontaneous. This will always be positive. Delta G will always be greater than 0. Okay? And now when we flip it, so this will be a negative number, and we'll be subtracting a positive number. This will always be spontaneous. Spontaneous. And the reason is, it's always going to be negative. Delta G will be negative no matter what. Okay? Finally, a negative and a negative. I'm just going to fill in. A negative gives us a negative delta G. We're going to subtract by a negative number. Once again, it is temperature dependent. And at low temperatures, delta G will be greater than 0. Delta G will be less than 0, because at low temperatures, enthalpy, delta H, will be the predominant part, and since that's negative, it's going to help us. And I've kind of spoiled number 3 by explaining which of these describes a favorable reaction. When delta G is negative, we have a spontaneous reaction, which is favorable. Okay. For which K does delta G indicate a favorable reaction? So K here is the equilibrium constant K. Constant. And just a reminder of the formula from Gen Chem 2, delta G is equal to negative RT times the natural log of K. R being the ideal gas constant, T is temperature, which is in Kelvin, and then the natural log of K, which is the equilibrium constant. So if a favorable reaction is negative, this is negative, so we need this part to all be positive. R is positive, temperature in Kelvin is always positive, so we need this thing to be positive. In other words, K should be greater than 1 for that to happen. When K equals 1, we get when we get 0, and when K is less than 1, we get negative values for the natural log, which will turn the thing positive. Okay. So rank these states of matter by entropy with the highest entropy first. So if we think of entropy as disorder, then the most disordered state of matter is the state of matter in which things are kind of flying around most crazily, if that makes sense. And that would be a liquid, not liquid, excuse me, a gas. If we think of the most ordered thing, it is the thing in which things are relatively stationary, nothing is shaking or moving excessively, and that would be a solid. And so the answer to this one is D. Okay, so this week only took about an hour because I did try to keep it a little shorter. Don't worry, next week will be kind of a lot more. We'll be talking next week a lot about kind of a review of delta G and kind of the different variations of delta G that you'll be seeing. We're going to get into a lot more of the formulas that we deal with. We're going to use the formula some of the formulas that I've just written out that relate to delta G. We're going to talk about some plots, and we're going to start dealing with some kinds of the concepts of some reactions. Then we're going to talk about amino acids. So next week is a bit of a longer one. Okay. I hope that you all enjoyed or benefited from this. If you have any questions at all, please come to drop-in tutoring anytime between 11 and 8 on Monday through Thursday, or between 11 and 5 on Friday or Saturday. Thank you all so much for coming. I hope you have a great week.